generous support and hospitality. And then I need to turn it on. Sorry. My postdoc Rudolf Sikora, who contributed to this work by carrying out actually very difficult analytical calculations. And I want to say that I devote this talk to the memory of Professor Tomas Brandes, who was my good friend, and we have collaborated for quite some time, and who died suddenly, I think in February this year. So this goes to memory of Tobias, and it's not an accident because actually this work is motivated by his work. So I got into this problem by seeing a poster by his PhD student some 5 years ago in Dresden. So I'm going to speak about a non-equilibrium heat transport in an exactly solvable quantum critical model. And so outline is here. I probably won't go in much detail through that, but nevertheless, I will spend quite some time on first motivating why I study such a thing, and then introducing basically the transport concepts, because I'm not sure how much it's kind of widely known in the audience. And then I will introduce an exactly solvable model for this transport, which is based on transverse field Ising chain model, and then show you some glimpse of the analytical solution, and then I will analyze the solution, which is somehow a little bit surprising. We got something different from what I expected. And I think that this will relate to the general topic of this workshop, because it's really very much about the finite system and how you properly actually should do the thermodynamic limit. And as you will see, I will actually contrast two kind of results, and one of them is quench, which is directly in the title of the conference. So I think this is the kind of the best match talk to the conference in the series with Klaus. I usually was very much off the topic, but this time hopefully it won't be so bad. Okay, so the motivation is the following. Some 10 years ago, there is a first paper I'm aware of at least, which is from the group of Tomáš Prosen in Ljubljana, who studied numerically heat transport through an XY Heisenberg spin chain by attaching leads to the end of this chain. And what he studied, among other things, was a correlation function of two distant spins in this non-equilibrium steady state which forms. And he found, as you can see in here, kind of a power law dependence of the correlation function on the distance, which is like a hallmark of some critical behavior. So that's one paper. So I was aware of this paper, but it did not catch my attention enough to really look into this in more detail. But then there was another paper from Tobias's group by Multifocal primarily, whose poster I saw just a few months before it was published in Dresden. And what they studied was this kind of system. So this is the transverse field Ising model. They put it into the circular topology, so to speak, and they attached the, actually these were bosonic at the time, so some bosonic heat baths which were coupled uniformly to this circle from one side, so to speak, was a hot bath, and from the other side there was a cold bath. It's a strange topology, especially if you want to make a thermodynamic limit on that, but just for sake of the model, why not? I study actually something slightly more meaningful, but or say a little bit more realistic. But as a matter of fact, the findings are exactly the same. And maybe I should make a disclaimer. Even though I will relate once to an experiment, this is like a purely theoretical model study trying to clarify concepts, as a matter of fact. So I don't care about being realistic at this point. I think that would be the next step. Okay, so they had this model given by this Hamiltonian. This is the exact spectrum of the model. It can be solved exactly by fermionization. And what they found, that finally caught my attention. They studied the energy current as a function of this phase parameter S. It's basically the control parameter, which is ratio between these two parameters of the model. And for this parameter S equal 1/2, one gets the quantum criticality. That's the critical point of the model. And they studied the energy current as a function of this phase parameter. And this was done for small systems like 440, but then they took the analytical thermodynamic limit and going to infinity. And what is probably more interesting is actually the second derivative of this heat current with respect to this phase parameter and with respect to the control parameter, which is shown in here for the same set of data. So you see that for really small systems, there is absolutely nothing happening. But as you increase the size of the system, there is actually singularity developing. And it's a logarithmic singularity. And this is exactly analogous to an equilibrium property. So at 0 temperature, for example, the energy of the model has logarithmic singularity at this point as 1/2. And their conclusion simply was that, okay, as a matter of fact, we can take this quantum critical model, we can attach it to baths, and both of them are actually at finite temperature, and you get a logarithmic divergence at the quantum critical point in the heat current, which sounds somewhat suspicious. So I came to Tobias, and as kind of usually I told him, look, Tobias, this is like pure bullshit, forget it. And when we started to discuss, and that was nice about energy current. No, it's a current. It's not it's not linear response. It's full current. Yeah, the parameter is the ratio of the exchange term and the magnetic field, and 1/2 is the critical point of the model. Okay, so that was nice about Tobias because he could withstand my, sincerity that I was coming to him, okay, repeatedly saying like, oh, this is complete nonsense, and we had very nice discussion then. Actually, I've enjoyed a lot discussing with him. So I looked into this problem because it looked seriously suspicious, and I knew accidentally that there were previous works actually on similar topics. So this is more than 10 years old, and I talked to Aditi Mitra when she was working on it, and they actually did study how quantum criticality behaves in an equilibrium. And their finding was, and I think it's shown here, that basically if you put a quantum critical system out of equilibrium, it becomes a classical critical system. So you develop an effective temperature, and there is no quantum criticality there. So I knew this result, so that was one reason why I was suspicious. But I should say that this is a more complicated model. This is some itinerant fermion system which has quantum critical point. There is many body interaction there between the fermions and so on. They used perturbative RG for getting this result and so on. So you may doubt, is it really so or not? The other problem I had was that I'm primarily working on transport in nanostructures. So it's like, from the point of view of dimensionality, these are finite systems, like zero-dimensional systems. And there the point is that once you couple them to the leads, you broaden the levels. You always do. And since master equation doesn't include the broadening the level at the stage of approximation which was used by them, I was suspicious because I thought, okay, well, there will be some broadening, and that of course can change these analytical properties, because if you have sharp levels, you can have singularities. If you have broadened levels, you should not have singularities. And that was actually my intuition that this is not gonna be true. And the reason is that if I actually treat the coupling to higher order, then this will just disappear, this effect. But for that reason, to show that, it was necessary to find a model where I could go to higher orders, and ideally to solve it exactly. So I have devised a model which I will introduce shortly, but just a crash course on transport here. This is taken from a textbook written by my ex-supervisor in Copenhagen, Carsten Flensburg, where he explains the tunneling experiments. And all what I want to show is that if you measure tunneling current, then by there is a formula how you get the tunneling current. If you take the derivative, so it means if you take the non-equilibrium conductance, you actually can probe the local density of states, say on the surface or close to the tunnel junction, which is kind of depicted in here. So this would be the density of states of the system you want to measure. Then you have some metal tip by which you probe it, and you get some convolution. If you make a derivative, then in fact actually the differential resistance, or sorry, differential conductance basically tells you what is the local density of states. No. Here it's just here it's like an STM or tunnel setup basically. What I just want to show is that I want to get to the transmission coefficient and the relation to the local density of states. Okay, so if you do a tunnel experiment, which of course has been done long time ago on various systems, and now it's routinely done in STM, what you get if you measure, say, with an unstructured one of the systems, then the differential conductance is giving you the tunneling density of states of the other system, which is or might be proportional to the local density of states. Okay, that's basically all what I want to show. And this was basically the message of Tomas Novotny, because then he has a long paper on the same problem, and their conclusion was you should look at the thermal transport in such systems, and essentially you should be able to see quantum criticality from the currents or say conductance as well. Okay, so transport setup is used for measuring, say, surface density of states. That's the message of this slide. Moreover, if you have a system where the electrons don't interact, or you can treat them as non-interacting, meaning that it's basically just mean field interaction, then you can describe the transport through the system basically just by transmission coefficient. So it's like an electronic waveguide, and all what matters is the transmission coefficient. And what is shown in here is actually derivation of the so-called Landau-Buttiger formula in 1D. Turns out that the material quantities like the Fermi velocity just cancel out in this formula, and what you are left with is basically the current is proportional to the voltage difference times the transmission. So the transmission is like the most important quantity you want to know in case you deal with the non-interacting transport. Okay, so this was the crash course on transport. It can take 2 semesters at least to do it properly, so I'm sorry this had to be really simplified a lot. And now the model. So what we study is the following. I took the topology of a chain, so it's really a transfer field Ising chain, and I couple it to 2 reservoirs at different temperatures at the ends of the chain. And as a matter of fact, I can choose what will be my reservoirs, because it should not really matter what are the reservoirs. They should be just characterized by their temperatures. So what I do, I actually choose chains which after fermionization just lead to non-interacting electrons. So like the standard in electronics, like the standard Landau-Buttiger reservoirs, so to speak. So I have 2 chains, which can be like XX chains, which can be fermionized to free electrons. Then I have my, or Tobias's, transverse field Ising chain, and then on the right-hand side, again, I put a chain which can be fermionized to non-interacting electrons, yes. Yeah, sure, that's what I'm saying. Okay, I'll show you what it can do, okay? If you just wait a little while, you'll see what can happen. Okay, I just wanted to say that this looks very academic, and it is very academic. But as a matter of fact, this model was more or less experimentally realized in this paper relatively recently. Of course, this is an equilibrium study. I'm not saying that the non-equilibrium experiment has been realized. It's not, but at least this model somehow can be at least partly realized in an experiment. Why partly? Because the critical point is here, and you can see that it's actually covered by some 3D order, so you get only into the critical region, but not to the critical point. I mean, in reality, it's always hidden somehow. That's just a detail. Okay, so now very fast, I will just run through the solution. If you get sleepy, wake up after like five slides, I think then there will be like physics coming. Now it's mathematics. So this system can be fermionized, as I said already, and as it's well known. And essentially, this is like a BCS Hamiltonian. So you get anomalous functions, you get interactions which look like this, C-deck. This can be, of course, diagonalized by the Bogoliubov transformation, and we can find the, say, Green's function, which in K is really trivial. That's just the inverse of this matrix. I need it in the real space, so I mean in lattice. So this can be done by the inverse Fourier transform. It still can be performed analytically, which I think is quite nice. So in particular, what we need is the like local element of the resolvent, and then we need a transfer matrix. But before that, this is the local element of the resolvent, and what is important is that there are bands. So this is a system with bands, and the bands go from minus 1 plus g to minus absolute value 1 minus g, and the opposite on, from the zero energy. So you can see that g, which is the ratio between the exchange term and the magnetic field, or actually vice versa, and g is 1, the gap closes, and that exactly corresponds to this quantum critical point. Okay. That was for an infinite chain, but as I'm saying, I have finite chain, which I couple to reservoirs. So to get the Green's function for the finite chain, and in particular, these are actually Green's functions on the interfaces. So this is the left interface, right interface, and this is like the cross term. You see that it becomes a little bit more complicated, but essentially the physics is nothing but some Andreev Fabry-Perot-like interferometer. So you have many, you have kind of infinite chain of back reflections in between the two interfaces. So it can be solved in principle. It's becoming sort of nasty if you will not treat it analytically, but it can be done. Once we have this finite chain system, we can attach the reservoirs, and this is done by this formula, which is some kind of like Dyson equation. And we attach it to left and right reservoir with this gamma left, gamma right tunnel coupling to the given reservoir. From that, we get the Green's function and can calculate the energy current. This is, again, this Landau-Buttigieg-like formula with the transmission coefficient. And since it's an energy current, there is one extra omega for integrating the energy, not the particles. Okay, these are just the Fermi-Dirac distributions of the two leads, which are characterized here by the temperatures. And most important is that there is an analytic expression in terms of these Green's functions for the transmission coefficient. So that's the way of solving it. And now I will show you if I do the generalized master equation limit. That's the limit when the coupling to the leads is very, very small, so it's infinitesimally small. And I only treat it in the lowest order. So the transmission is proportional to the small gamma. The small gamma is actually the gamma left, which equals gamma right, equals gamma. And it's small, so it's proportional to the small coupling. And then there is an analytic formula which depends on the coupling strength or this critical parameter and frequency. And close to zero frequency, that's where the gap is closing, so that's where it's interesting for us. It has this analytical form, okay? And it's shown in here, so this is a cut for two values of this critical or the control parameter. The yellow line is the critical point, okay? So the transmission looks like this at the critical point. Away from the critical point, there is a gap. Here is the second derivative with respect to g of this function as a function of g and the energy. And you can see that it has some singularities. The white is like very high value. So it has some singularities at the bend edges, and really here at the critical point, there is something going on at 0 frequency. And now, actually, which one? This one. Now we actually study really the current, or more precisely the second derivative of the current with respect to this control parameter. And first we do it numerically, because this is the transmission. You can see that this is for n, I don't know, 40 or 50. You see that there are these Fabry-Perot resonances, which get denser with the number of chain lengths. So it's kind of crazy function, but you can integrate it. You can integrate it numerically, and then you take the second derivative. So this is done in here for 2 values of the coupling parameter, and for much larger n. Here you wouldn't see anything for this large n. So this was done in here, and the result from the GME is the blue line in here, and it was put into the same numerical routine in MATLAB as this finite n results. And the reason why I show it is the following. This should be logarithmic singularity analytically, or this is logarithmic singularity analytically. But MATLAB thinks it's this, actually. So this is just to compare that you see that for finite gamma, even though it's not too large, this actually seems to be pretty much the same as the logarithmic singularity. So that was a bit surprising for me, but this is just numerics, so that was not enough. So it's an analytical result for the transmission coefficient put into the numerical routine calculating the second derivative. And since a numerical second derivative, it simply doesn't give the divergence, it gives this kind of behavior. Okay? So this is just an indication. It looks like even finite coupling gives the same as GME. That's all what I'm saying at this point. It's not proven yet. So we needed to find really the thermodynamic limit. And at that point, I involved Truda, and he did really a great job, because what was necessary to do is essentially, the procedure is the following. You have these very fast oscillations in the transmission, and the thermodynamic limit means that you integrate over these fast oscillations, and that's basically carrying out the thermodynamic limit. Sorry. The same approach was taken for phonons by Joel Lebowitz already some 5 years ago in this PhysRef-E, so we do exactly the same as he does. Since he's a mathematician, I feel comfortable because I don't have to verify integrable majorant and stuff like that. I just do the same as Joel Lebowitz, so I should be on the safe side. And what we find is this result, and this result is very surprising because it's telling me that the behavior is exactly the same as the master equation, apart from a prefactor which depends on the coupling to the leads, but it absolutely doesn't depend on frequency nor the control parameter of the model. So it means that indeed what we have seen in here, that the finite coupling looks analytically pretty much the same as the GME, is really proven here analytically, and indeed there should be a logarithmic singularity there. Now that was a bit shocking, because this confirms Tobias's result. There is a singularity, and now I have proven it for an exactly solvable model, and it kind of goes against my intuition. Even worse, there was a paper by Doyon and Denis Bernard back in 2013 where they study exactly the same model, but they studied in a kind of, the setup is slightly different. They say, well, let's take infinite chain, split it in 2 halves, and then you thermalize 1 half at certain temperature and the second half at another temperature, and at certain time you make a quench, which means that you join these 2 halves of the chain, and there will be some transient effect, of course, but then some sort of stationary or quasi-stationary current just develops, and this can be considered as the non-equilibrium steady state. And they solved this, and they found an expression for the current. Now it's a function of the two inverse temperatures, you know, in terms of these junctions, which are just some d gamma functions, so something horrible. It looks really horrible, but as a matter of fact, if you look at it, this just means that they say that the transmission coefficient is 1 in the band. That's all what this says. If you integrate that, you get this kind of nasty functions. But as a matter of fact, what they claim is trivial. They say the transmission coefficient is 1 within the band. Okay? And so this is analytical result. And I took the second, so this, sorry, there are no description of the axes, but again, this is the second derivative of the current with respect to the control parameter as a function of the control parameter, which they call H, I call it G, and in this language, it's at 1 is the critical point. And what you see here, and this is for two values of J, which is like the bandwidth, which I said 1 in my approach. But what you can see, this is analytical, so this is not like previously that there should be singularity and there is not because of the numerical error, but here it's finite, and this is an analytical result. So there is a kink in the second derivative, which means that the third derivative will have a jump and so on, but there is no singularity, no logarithmic singularity. So even worse, you know, first I confirmed Tobias's results, which go against my intuition, but then actually I find that there is a paper on essentially the same model, finding something completely different. So that was somehow puzzling, and to some extent it still is a little bit puzzling. So obviously there are like two approaches. One is this standard transport setup. You take two reservoirs, you couple them to the system, and you look at the current. And the other one is that you just split the system in half, and then you thermalize the two halves differently, and then you join it, and you make a quench, and then you look what is the quasi-stationary behavior, and you get something completely different. So there could be like two things how to simply reconcile it or how to understand it. The first one is maybe the problem with the transport setup is that I have V-coupling to the reservoirs. So, you know, if this gamma is large, then this should be like it's more thermalized and so on, so it should be better. But as a matter of fact, no, because it gets even worse. If gamma is very large, just remind you that this is proportional to gamma. So even if this is proportional to gamma, for large gamma, this actually goes as 1 over gamma, which is some kind of like Zeno-like effect, or I don't know. It's simply, if you have very strong coupling, actually it doesn't go to 1, but it goes to 0, so even worse. So there is no simple connection just by tuning this coupling parameter, obviously not. The second one, which looks more promising, is how about the coherence? Because, of course, what I showed you for this finite n, we have all these Fabry-Perot resonances which are given by the coherence, you know, going from one interface to the other and so on. So that's definitely coherent. On the other hand, the quench is definitely not coherent because you thermalize the two pieces differently to different temperatures, different reservoirs. So this won't be coherent. So maybe this is just a level of coherence, that one result is coherent, the other one is not. But the problem is the following. If you have two interfaces, and now let's assume that you have incoherent transport, so then if single interfaces transmission T means single interfaces reflection R, then you can sum this up. This is probably even secondary school problem or some very early university problem. You find this result, and we can, and Ruda did, we can calculate the transmission of a single interface for arbitrary coupling, and it turns out that if we calculate the exact transmission of a single interface, we plug it into this formula, we get what we got for this full setup in the thermodynamic limit. So as a matter of fact, even so, we make a limit of n of coherent problems for each finite n. It was coherent. When going to this thermodynamic limit, when we integrate over these fast oscillations, we actually go to incoherent limit altogether. So it's not a problem of coherence either. So what have we achieved? So first of all, I've shown analytically that these singularities in the current indeed do survive even for finite coupling, and this is an exact mathematical result. So this is not an artifact of Tobias's GME, as I had thought before. Second thing is that in fact, these singularities must be caused, obviously, by singularities which happen at a single interface transmission. Because the full transmission is basically just given by the single interface transmission, by incoherently connecting them together, which is this formula, which is kind of nonlinear, but still, I mean, all the singularities are already contained at the single interface. And that means that this must be somehow fully determined by the boundary conditions. And therefore, I was still right telling Tobias that this was nonsense, because he claimed that he was able to kind of probe the many-body quantum phase transitions of the bulk system. But this is not the case, obviously, because if you do it with a quench, you don't see anything. So basically what you see is actually single particle interfacial resistance, which has, which is related to the interface, not to the bulk material there. So as a matter of fact, you don't probe the many-body quantum phase transition, but this is known under the name of electronic topological transition. This is well known in the single particle physics, and there was like a review by Jaroslav Blanter nearly 25 years ago already. Probably the most famous one is the Lifshitz transition. This is known. And this is just related in single particle picture to change of the topology of the Fermi surface. In other words, and now I come back to the local density of states, if you go through a singularity of a local density of states, you would see such effects. And here it's such that the many-body quantum phase transition induces these single particle singularities, but it would be false to actually make, if you see these transport singularities, it would be a false conclusion to say that there is a many-body quantum phase transition inside, because you can get the same effect by different means, which are purely single particle. Still, what remains a little bit mystery to me is how comes that these two approaches are really so vastly different. I'm not sure why I still don't have full grasp. I have some guesses, but I don't have full grasp of why the quench and this setup is so, vastly different. You get completely different results for the transmissions. And the reason why I'm a bit puzzled is because this wideband limit and large coupling limit is routinely done in quantum transport, I think in the belief that this is as close as to this Landauer adiabatic reservoirs assumption as it can be. But obviously here it shows that it's not. Okay, thank you very much for your attention.